So this lecture is going to be discussing chi-squared and specifically computing the goodness of fit chi-squared. So we will be going through the steps in computing the goodness of fit chi-squared. So for this, you should be able to compute chi-squared and apply chi-squared. And you should understand how the application of chi-squared works, and particularly goodness of fit chi-squared. So let's just go over, let's review real quick what the goodness of fit chi-squared is. So it examines the difference in frequency of group membership for one categorical variable. And the logic here, it analyzes the observed frequency of a group versus the expected frequency of groups. So we have 4 steps in this process. Step 1, state the null and research hypothesis, right? So this is a very common step. Step 2, define the critical region. Step 3, compute the test statistic. Step 4, interpret and summarize the results. So we'll be going through each of these in this lecture. So let's give an example. This will be our running example for this lecture. Dr. Collins is interested in knowing whether there's difference in the class year of his BIS 315 students, where the variable class year is a nominal variable split into 4 categories: freshman, sophomore, junior, and senior. Okay? And here's our data. So these numbers here, 2, 4, 16, and 10, those are the frequencies. Just to note, these aren't actual data, so I don't even know if I have your class years, but so this is fictitious data. So let's say there are 2 freshmen in the class, 4 sophomores, 16 juniors, and 10 seniors. So the important things to note here is we need to know the number of groups or categories. In this case, we're going to have 4. And we need to know the number of students across all groups. So this is our sample size, right? So our N, what we've been using for sample size for quite some time now, throughout the whole class. So step 1, we need to state the null and research hypotheses. And we have 2 potential options in this case. Option 1, we can hypothesize the observed frequency, and what the observed frequency is what the data, what our data show, right? That's the actual frequency we have, versus a hypothesized frequency. And the hypothesized frequency is usually based on some other piece of data, right? So let's give an example. So this is so the observed frequency of what we have currently versus what we had in a previous class, right? So say I'm asking the question, do freshman, sophomore, does class year differ this year than what it was last year when I taught the class? Something like that, right? So we have some other data to base it on. So yeah, so it asks, are groups significantly different than what they were last year, right? So that's an example. Option number 2 is hypothesize the observed frequency, so what our data show, versus chance, right? So just chance that somebody would fall into that group, picking a number out of a hat, for example. So this is, again, the difference between the observed frequency and chance. So this asks the question, are groups significantly different than what would be expected given chance? Or in other words, are the groups significantly different from one another, right? So you should, given chance, have an equal opportunity to be in any one of the groups. So in this case, you're really asking, do the groups differ from one another? So in this case, let's take option number 2. Let's just see if there's significant differences across groups, right? Given chance. So in our case, the null hypothesis always states that the frequencies are equal given chance. So an example would be the proportions of each group are equivalent. They're the same. That's the null hypothesis. Research hypothesis, on the other hand, hypothesizes that at least one group is significantly different from another group. So here, the proportions of each group are not equivalent. So what we're saying here is that there are differences across groups. So those are the null and the research hypotheses. Then what we need to do is move on and define the critical region. So the critical region, just like the other tests that we've talked about, include degrees of freedom. And in this case, degrees of freedom equals the number of categories you have minus 1. And we find our critical region using our Appendix G in the back of the book. And that's this little table down here at the bottom right. And we want to use our alpha level of 0.05. If you want to be more conservative, you can do 0.01 if you'd like, but 0.05 is sort of the standard. That gives us 95% probability that the result is beyond chance. So it gives us a good chance of saying that our results are correct without error. So in our case, right, we have 4 groups, and 4 minus 1 is 3. That gives us our degrees of freedom. We have our alpha level, right, so it's the same thing as we just saw up here, alpha at 0.05. And to find the critical region, we just bring the row and the column together, and that gives us our critical region of 7.815. So just like with t-test, just like with ANOVA, what we're doing is when we run our chi-squared test, we're asking the question, does our statistic fall beyond this critical region? Is it greater than the absolute value of this critical region? So now we need to compute the chi-squared statistic. And again, this is the goodness of fit chi-squared statistic. So what we have here is our observed frequencies versus our expected frequencies. So what we need to do is determine the expected frequencies. And what we do for this is we just do a simple calculation by chance. And what that means is we take the number or our sample size and divide that by the number of groups. So in our case, we have an n here, and we divide that. Our sample size is 32, and we have 4 groups, so we divide 32 by 4. That gives us 8. So that means by chance, if any given chance, we should have roughly 8 people in each group, right? And so our expected frequencies are these italicized numbers right down here. And those are important because we need those for our calculations of the chi-squared statistic. So now we need to compute the obtained value. So our obtained value is our actual chi-squared statistic. This is the value we're going to be using to compare to the critical value. And the equation for that is, so this little x2, that represents chi-squared. The equation for that is the sum of this equation here. So we have to do this for every single cell, right? So the sum of the expected frequencies minus the, let me start over. The sum of the observed frequency minus the expected frequency squared divided by the expected frequency. And so what we do is plug these numbers here. So this is for cell 1, so this is freshman, this is the equation for freshmen, this is the equation for sophomore, juniors, seniors. And we add, when we get all those together, we have 4.5 plus 2 plus 8 plus 0.05. So our final answer here is 15. So we sum all those numbers up, we get 15. And so what we find is that 15 is greater than the critical value of 7.815. So what do we do in this situation? What do we do when our chi-squared statistic or test statistic is greater than our critical value? We reject the null hypothesis. Okay? So what we're saying is there is a significant difference across these various groups. So now we need to interpret and summarize the results. So there are several elements we need in this interpretation and summarization. First, we need the chi-square statistic. We need the degrees of freedom. So in this case, our degrees of freedom equals 3. We have 4 categories minus 1, that equals 3. Our n is 32. And our p-value, again, this is our alpha level. So this is usually 0.05. So we're saying in this case, it's either greater than or less than 0.05. And so what you'll find is, so what we need to do is interpret these results in words that can be understandable. So here's how I interpreted them here. You may want to take a stab at interpreting these results yourself. So you can pause this if you'd like, go back and write down the results and try to interpret this yourself. So what I found here is that a chi-squared, and this is what I would write, a chi-squared test was conducted to examine whether students in BIS 315 are equally distributed by class year. Significant differences were found across class year, with a chi-squared of 3n equals 32, and the chi-squared equals 15, and we have a p-value of 0.05. And so what we have here is our chi-squared statistic, we have our degrees of freedom, we have our sample size, our n, and we have our p-value. So these are all of the elements you're going to need to put into an interpretation of a goodness of fit chi-squared test. So now understanding this, you should be able to compute a goodness of fit chi-squared statistic if you're given a frequency table, and you should be able to apply or understand how to apply a chi-squared statistic. And so moving forward, what I want to do is I want to provide a practice problem, and I'll give you the answer to the practice problem, and so I'll leave it up to you to try to compute it, or to work on computing it. So you want to know whether UWB students differ in how they commute to school. You have asked 95 students if they either walk, cycle, drive, or take the bus to school, and place them into categories. You have the following data table. So 25 people walk, 27 cycle, or ride their bike, 26 drive, and 17 take the bus. So the final answer for this chi-squared statistic is 2.648. So go through each of the following steps, or each of the steps you saw above. Step 1 through 4, do the NULL and research hypotheses, define the critical region, compute the test statistic, and interpret the results. Okay?